All right, hello everybody. Round two here as I recorded this whole video. None of the audio recorded, so hopefully this one works out. Today we're going to be doing osmosis, talking about the movement of water in and out of the cell based on different solute concentrations, as well as looking at electrochemical gradients a little bit, and we'll be learning some new math, so that's always fun as well. All right, so in a previous lecture, we talked about chemical gradients, which is this idea that if you have an uneven number of molecules on both sides of a membrane, it's going to flow from high concentration to low. It's not to say that no molecule will ever flow from low to high. It does happen. This is just random movement of molecules due to energy and free space. But overall, the net movement is going to be from high to low as these concentrations tend to even out over periods of time. Now, another type of chemical gradient that we have to be aware of is an electrochemical gradient. This is where you still look at the chemical gradient. So, for example, potassium is higher on this side than this side, so you would think potassium will naturally flow from here to here. However, in some cases, especially for proteins and ions, it's not always that simple. These ions and proteins also have a charge to go along with them. So whatever side of the membrane they're on, they're also going to create a net negative or net positive charge as well. So for example, on the left side here in the extracellular part of the membrane, we have a lot of positively charged ions. So this side of the membrane has a positively charged chemical property to it. While the intracellular part is mostly negative in terms of proteins and chlorine. So this is going to have a net negative chemical property to it. So molecules that are positive are going to want to tend to flow to this way, and places that are negative are going to want to tend to flow to that way. Okay, so we can use electrical charges as well for these gradients. Now, another type of concentration that we have to be aware of is something called osmolarity. And osmolarity is going to be your total solute concentration in a solution. So solution is essentially you're mixing solids into liquids. Solvent is the liquid, solute is the solid. A good example of this would be like salt water. So solute being salt and solvent being the water, and you can mix it in. Well, osmolarity is going to be the concentration of that solute within that solvent. So how much salt, for instance, are you going to put in the water? All right, so it has to be a concentration unit. So think of things like moles per liter, which is typically what we're going to do, moles being a way to count molecules. You could also think of things like percentages or, mass per unit of volume, things like that are typically going to be how this is going to be measured. Now, when we want to compare the osmolarity of two different solutions, we're going to do that with something called tonicity. It's important to remember that tonicity is a measurement of relative osmolarity, which means it's a comparison measurement, which means you can't just look at one solution and say what the tonicity is. It's always got to be in comparison to something else. Any side, when comparing a solute, in this case, we're going to compare the inside of a cell to the outside of a cell. Anytime you have a higher concentration, that is going to be referred to as the hypertonic side. And then the side with the lower is going to be referred to as the hypotonic. You cannot have a hypertonic solution unless you have a hypotonic solution to go with it. Because by definition, you can only be hypertonic when compared to something else. So in this case, hyper inside the cell, hypo on the outside, and then over here, it is hypo on the inside and hyper on the out. Okay? Now, you can also be isotonic, and this is where your solutes and your solvent are at an even concentration both inside and outside the cell, or for whatever two solutions that you are comparing. Now, the reason this is important is because it's going to tell us which way water is going to want to flow. Water always wants to flow from hypo to hypertonic with the goal of evening out the two concentrations. So if I wanted to lower the concentration of solutes in this solution, adding more water is going to make this smaller. So water will naturally flow from hypo to hyper until both solutions are even and the net movement of water is the same. Now, when plants and animal cells enter different states of tonicity, they're going to react differently. If an animal cell enters a hypertonic solution, it's going to shrivel up or plasmolized, which essentially means that it's going to shrivel up. Typically, we only use this when we talk about plant cells. In animal cells, we typically refer to it as shriveled. You'll notice in the plant cell here that the cell wall kind of helps it maintain its rigidity, as opposed to the animal cell only has a cell membrane, so it tends to just shrivel up. In hypertonic, animal cells will take in a lot of water, and this can sometimes cause the cells to explode, which we call lyse. In plants, essentially the cell wall will help it maintain its rigidity, essentially reducing the chance of this lyse thing happening. And this is going to increase the turgor pressure that we talked about in Unit 1. And in isotonic, the water moving in and out is net zero. So we're going to essentially have normal cells in this case. Now, we can mathematically represent water potential, which is going to be a measurement of how water is going to want to move by osmosis. So in this case, water potential is calculated by adding the pressure potential and the solute potential. We'll talk more about what these are in the next few slides, but essentially, this is just going to tell us which way does water want to flow based on solute concentrations and atmospheric pressure. Now, the measure of a water's tendency to move is going to be known as osmosis. So the first one we're going to talk about here is the pressure potential. Your pressure potential is essentially just asking how much atmospheric pressure is the water under. If it has positive pressure, that means it's above atmospheric conditions or typical atmospheric conditions, causing it to be pushed down and the other side to go up. If you have lower air pressure than atmospheric conditions or typical atmospheric conditions, that water is going to flow up in comparison to the other side. So how much air pressure the system is dealing with is going to be one thing that helps direct the flow of water. The other one, which is the one that you're mostly going to work with in this class, is going to be the solute potential. This is essentially a measurement of how much are these solutes more or less pulling that water to their side. So we're going to have four things that we need to multiply to calculate our solute potential. The first one is the ionization constant. Now this is going to be different for each molecule that you'll be looking at, but essentially the higher the number, the greater the pull it's going to have of water. So sucrose has an ionization constant of 1. Table salt or sodium chloride is going to have an ionization constant of 2. Anytime you have a question with this will always be given to you, so it's not like you have to memorize any of these. Next, we have the molar concentration. This is essentially a measurement of how concentrated is that solute in the solution. Next, we have R. This is just going to be a constant. So no matter what equation you're doing with, whatever problem you have with this, R will always be the same. You never want to change this. And then the last one is going to be T, which is temperature. Please realize that the temperature is in Kelvin. So when we calculate this, if it's given to you in Celsius or anything else, you do need to convert it. So I'm going to go ahead and give you guys an example problem, and then you can attempt it tonight, and then we will go over it tomorrow. So it says, what is the water potential of a 0.5 molar sucrose solution at 21 degrees water in an open system? The solute concentration of sucrose is 1. Now, whenever a problem says it is an open system, that means that the pressure potential is going to be 0. 0 for that, okay? Also, don't forget to convert Celsius to Kelvin when you attempt this. So go ahead and give this problem a try. We'll go over it tomorrow, and I will see you then.